Hello everyone, this is the first class of digital systems, okay? Um, Last time we just covered the syllabus, that's why it was just administrative stuffs. For from now on, I would like to cover the details about the combinatorial logic circuits and its related Boolean algebra and gate logics and so forth. So this is kind of a quick start for this class. So before starting Boolean, logics, gate, and algebras, I would like to let you know what is the digital systems at first. So here, you can see a lot of digital systems. Those are existing our daily lives. So cell phone, CD, laptop, tablet, camcorder, and so forth. These are all digital systems. The opposite meaning of digital system is the analog system. Analog system is just capturing the analog signals in your daily life. But in order to save the data into our digital system, then we need to convert the analog signal into digital signals. So in CD, we have a lot of characters inside there. A, B, C. We can store these kinds of characters inside this CD, but these are all organized by ASCII code or the other code. So these are all organized by 0 or 1 digital signals. So if we can save some information into digital signals, then we can save the data into digital or electrical systems. So in cell phone, we have a lot of processing, we have a lot of store, we have storage inside there and so forth. Then we can process them with digital signals, or we can save the information in a digital signals. That's why digital is very important meaning in our daily electrical equipment. In laptop we save some information inside there. We are looking at something in front with in our LCD display. So in that case, we are saving information in digital 0 or 1, or we are looking at the information in a JPG or PNG format, which is also digital. So that's why every single data formats are all digital. uh, every single uh, every single information is all digital. So here we have tablet. Tablet is also kinds of PC. So we also have video camcorder, video camera. If you are using video camera, then you are capturing some scene or objective in analog at first in your eyes. And then if you want to take the picture of it, then you can push button of your camcorder or your digital cameras. Then you can save the analog information into digital image inside the storage. So for example, you are watching a mountain. Then you want to take a photo of the mountain. Then you use your digital camera. Then you are when you take the photo of the mountain, then you save the image of the mountain inside your digital camera. So when you look at the mountain itself, it has analog color. But if you take the picture of it, then it is digital image. That's why it contains digital pixels in order to represent the mountain. That's why at this moment, for taking the picture, you are now converting the analog into digital. Okay, that's why in order to save everything into your inside your system, or in order to process something, then you need digital related operation. So another example is a transfer block diagram. So here you have antenna, okay? So this is RF system such as Wi-Fi in your cell phone or laptop, or LTE in your cell phone or laptop. So when you are receiving a signal from Wi-Fi, you are receiving some radio waves or electromagnetic signals. So those are all analog signals, okay? So when you are receiving analog signal via antenna system, then the signal will go to TR switch at first. TR switch means transceiver and receiver switch. So in human body, if you want to talk something, then you are using your mouth. If you want to listen to something, then you are using your ears. That's why your transceiver and receiver are separated in your human body. But in your RF system or transfer system, you just use the antenna for your transmission or reception. That's why you need to decide every single time whether you want to transmit something or you want to receive something. That's why you need to switch every single time. That's why you need a TR switch. When you are doing transmitting, then you are using transmitter. When you are receiving, then you are using receiver, okay? But when both of case, both of case, when you receive some signal with 100 megabps, it means that you are receiving the signal 100 multiplication 10 to the 6 bit per second. It means that every single seconds you are taking 10 to the 8 bits of information. Okay, it means that you are taking this amount of bit every single second, but it means that you are just receiving electromagnetic waves from analog domain, and then here you have modem or transceiver which can translate into digital signal with this speed. So this is kind of clock speed in your transceiver system. That's why you are generating this amount of bit information in your transfer system. That's why this is the digital system. Once you convert every analog signal into digital signals, then you can start to understand what is this meaning, what is the exact meaning, okay? That's why converting the analog signal into digital signal is very important in our daily digital systems, okay? So today is kind of introductory class for the first week. That's why we will just cover binary logic, gate, and algebras. So you don't need to worry about too much. You just enjoy the class, and that should be enough. And first of all, I would like to let you know the basic logics in Boolean operation, and then we have to understand how we can represent them into some symbolic stuffs. That's why there is called gate. And then we have to understand the basic algebra in order to simplify the Boolean logic case. So we will gonna look at the details about that from next slide. So in binary system, you have three different Boolean logics. The first one is AND, next one is OR, the last one is NOT. Okay. Okay. So here, AND means that you have two input signal X and Y. So if you have AND between them, then you have to calculate the AND. AND means that you will gonna generate true when your inputs are all true. So this one should be true, this one should be true, okay? So this is the logical meaning of AND. So you can refer to this figure. So in this lecture, in this textbook, in this chapter, 0 means false, 1 means true, okay? So in this case, the last component, 1 and 1, means true eventually. So this will be true eventually. Otherwise, you will gonna be with 0 in some part, such as this one, or this one. That's why in this case, the result should be 0. This is AND operation. But if you are doing the OR operation, then you have X and Y. And if one of X and Y is 1, then you can say that this is true. That's why in this case, these are all true because you have at least one component inside X and Y. Then these are all true in this case. But if your inputs are all 0, then you're gonna return the false, okay, 0. Not is very easy. So when you have one input, this will gonna take the complementary of your input. That's why when you take the 0, then you will return 1. When you take the 1, then you will return 0. Okay, this is very easy. This is not. So in addition to the meaning, you have to understand the symbol in order to represent AND, OR, and NOT. So here you can see that when you have dot, which means multiplication in mathematics, then you are saying that this is an AND operation. When you have plus, then you are saying that this is OR operation. When you have a bar here, then you are saying that this is NOT operation. Okay. So here I'm saying that each signal only can get 1 and 0, true and false, okay? So then AND gate can be represented as follows. This is a logic gate. OR gate can be represented as follows, and NOT gate can be represented as follows, okay? So it is very easy to understand this one because this is looks like a D, just like that, okay? So this is smooth, that's why this is like O here. That's why you can memorize or you can remember the gate in this way if you want, okay? So this is NOT gate. So let me look at some more details about that. As I told you before, in order to represent AND operation, you can use the multiplication notation. That's why you have this one, okay? So in some cases, if you, I believe you already know that this can be omitted. That's why you just can write down X and Y. That should be enough as well. That's why this So in AND gate, you can just write down this one. As I told you before, this looks like a D. Okay. So AND is true only when all given inputs are true. That's why this is the only one case for true, and the others are all false. And this also can be represented as the multiplication notation. So OR notation can be denoted by plus notation, okay? That's why when you look at the plus notation, then you can say that this is OR. So OR operations are here. So here, this is smooth, that's why this is OR. And you have plus notation here, you have plus notation here. As I told you before, OR is always true when your input has at least one true. That's why these are all true and only this one is false, okay? So NOT is very easy. NOT is just a conversion of the Boolean notation. That's why if you have 0, then you have 1. When you have 1, then you have 0. Okay, this is NOT operation. In NOT operation, you are using this gate as n, you are using the bar on top of the x. But when you type this one in Notepad, this is not possible because you can put that in your notepad or you can write down this one in your notepad. That's fine. You can use plus notation in your notepad. That is also fine. But if you want to represent NOT operation in your Boolean operation, then you have to use these kinds of complement notation, or you have to use this prime. Then it means that this is NOT operation. Okay, so you have to remember this one in order to understand what's going on. So it's very easy and straightforward. That's why this is so fast. And then now you are ready to go for the Boolean algebra. So let me go further, more details about this one. Boolean algebra is kinds of algebra which is dealing with binary variable. So up to now we studied about the binary variable which is 0 and 1, okay? And then logic operation. We studied about this one, and those are all and, or, and not. So we have to, so the meaning of this first sentence is that from now on we're gonna study about the algebra which consists of and or not gate with inputs as 0 and 1. Okay, that's it. That's Boolean algebra. But here, this is somewhat different because the variables are designated by the letter of the alphabet. It means that the inputs are all alphabets. This is also alphabet. But as I told you before in the first sentence, I said that the inputs are all binary variables, 0 and 1. But these are all characters. What's the difference? The different thing is that these are all variables. So A can be 0 and 1, B can be 0 and 1, C can be 0 and 1. Then in this case, we have 2 to the 3 different cases. So we have to consider all these 8 different cases in order to understand the system, okay? That's why they are same to each other. And this is OR gate. In this OR gate, you have 6 different inputs, okay? That's why you are adding all of them. And then you are saying that you are doing OR operation with this given 6 inputs, okay? So let's start with this one simple example. Let's start with this one simple example. So in this case, we have 3 input, x, d, and a, okay? So we have x, d, x, and a. So and then x has negation. It means that not operation. That's why it has not operation at first. And then the end, the result has end operation. So this one and this one has end operation. And then finally, this result has the OR operation with A. That's why this one has OR operation with A. And the final result is denoted by L. That's why you have L eventually. That's why you can easily see that this equation is equivalent to this logic circuit diagram. So in your midterm exam, I may give you this function at first, and then I will let you do the translation into logic circuit diagram. Then you can do this one for sure, okay? Then after that, you have to understand the property of this system. That's why you have to consider 0 and 1 in D, 0 and 1 in X, 0 and 1 in A. That's why you have 2 to the 3 different cases for this system, totally 8. That's why you can organize the one table which can be used to understand this circuit. So that is called truth table. So as I told you before, we have 8 different cases. That's why we have 8 different cases. And in these 8 different cases, we have all combination of these Boolean notations. That's why we have all different cases. So for example, let me do this one, okay? So suppose that D, X, and A are all 0. So this is 0, this is 0, this is 0. So here this 0 goes to this negation, not operation. That's why this becomes 1. 0 and 1 are in AND. So in this case, the result should be 0. And now you have 0 and 0 in OR gate. Then in this case, the result should be 0. That's why the result should be 0. So this one shows the result of this logic circuit diagram. So let me do the other one, the last one. So in this case, you have, let's see, that's everything. Oh, let me do this one by one, entirely. So here, let's go to the second one. So in this second one, this is 0, this is 0, this is 1, okay? So X has negation, that's why this becomes 1. 0 and 1 are in AND gate, that's why the result should be 0. And then you have OR operation with 0 and 1, that's why the result should be 1. That's why the result is 1. So let's go to the next one. And then in this case, this is 0, 1, 0. So this has negation, so this becomes 0. 0 and 0 becomes 0. 0 and 0 becomes 0. That's why the result should be 0. Let's go to the next one. 0, 1, 1. So in this case, 0, 1, 1. So in this case, negation it takes 0 here. And 0 and 0, that's why it should be 0. And 0 and 1, that's why you have 1 eventually. 1. So let's go to the next one, okay? So here in this case, this is 1, 0, 0. So this has negation, this becomes 1. So 1 and 1 you have, that's why this becomes 1. 1 and 0, that's why you have 1 eventually, 1, okay? So let's go to the next one. So in the next one, you have 0, you have 1, 0, 1. 1, 0, 1. So this one has 1, this one has negation, that's why 1. The return value should be 1. 1 and 1 and OR should be 1 as well. That's why this becomes 1. So let's go to the next one. So in this case, this one has 1, 1, 0. So this is 1 and 1. That's why you have negation. That's why this becomes 0. 1 and 0 and becomes 0. 0 and 0 OR becomes 0. That's why this becomes 0. 1, 1, 1 means that you have 1, 1, 1. So here you have not operation. That's why you have 0. 1 and 0 becomes 0. 0 and 1 OR becomes 1. That's why this becomes 1. Then you can confirm that this truth table is correct. So when you have this one, you have to be able to make this logic circuit diagram at first, and then you can derive this truth table eventually. Then I can say that you understand this system fully. So then, this is more important, Boolean algebra. So actually, you can design these kinds of logic diagram. It's not that difficult, okay? When you have this one function, then you can easily convert this function into this logic diagram. So it's totally fine. However, suppose that this logic diagram is too complicated, and then you have another circuit which has the same truth table, but this is much more simpler, then this is much better, right? That's why you have to find this one in order to guarantee more simplification. Then you have to understand Boolean algebra in order to derive this result. So from now on, we will gonna study about the Boolean algebra. So these kinds of table means the Boolean algebra. These will be used for the simplification of the block circuits eventually. Let's go one by one. The first one, x plus 0 equals x. This means that you have OR notation here. So you have x and 0, and right hand side you have x. X can be 0 and 1, right? And OR is OR, 0 is 0, and you have OR operation. So then this becomes 0, this becomes 1, right? So in this case, x is here, those are same to each other. That's why those are same to each other. This is correct. Okay. So let's go to the next one for the proving. So here you have x dot 1. It means that you have x dot 1. X can be 0 and 1. 1 is just 1. So you have dot operation, which means that this is AND gate. So 0 and 1 AND becomes 0. 1 and 1 and AND becomes 1. That's why you can see that this is again x. They are same to each other. That's why this becomes x here. Then let's go to the next one, number 3. So you have x, you have 1. So x can be 0 and 1, 1 can be 1 and 1. Now you have OR operation. So then in this case, you have at least one truth. That's why this becomes truth. In this case, this is also truth, obviously. That's why you can see that this is just 1. Whatever we have in capital X, that's why this becomes directly 1. Okay, so let's go to the number 4, this one. So here you have x and 0. X can be 0 and 1. 0 is just 0 and 0. Now you are doing the AND operation. This becomes 0 because you have both of them should be 1, but both of them is 0. In this case, you only have at least one number 1. That's why this cannot be 1. This is just 0. That's why eventually this is 0. So this is 0. So number 4 is also correct. Now you have to go to number 5. So number 5, you have x or x. So x can be 0 and 1, and x and x. It means that you have the same thing. So 0 and 0. When you do the AND or, then this becomes 0 because you need at least one number 1 if you want to be true. But both of them is just 0. That's why this is 0. In this case, both of them are true. That's why this is true. This is number 1. So this is exactly same with the x. That's why this is same with the x. Okay. In number 6, you have x and x. That's the same to each other. So 0 and 1, 0 and 1. So when you are doing the AND gate, this becomes 0. This becomes 1. That's why this is again x. That's why you have this one in number 6. So let's go to the next one. So next one, so you have x and x bar. Okay, x and x bar. So x is 0, 1, x bar becomes 1 and 0. So now you are doing the OR notation. So OR, you have at least one number 1. That's why this is 1. You have at least number 1 here. That's why this is 1. So this becomes number 1. Number 1. So let's go to number 8. X and x negation, 0 and 1, 1 and 0. Now you want to do the AND gate operation. So then you can see that both there is no chance to be number 1 in both cases. They have 0 and 1 and 1 and 0. This becomes 0, this becomes 0. That's why this is just 0. That's why you have just 0. Okay. So here we confirm up to 8. So let's go to the number 9. You have x, 0 and 1. Now you have x bar. It becomes 1 and 0. Now we have another bar. You have 2 bars here. That's why you have another NOT operation. That's why this becomes 0 and 1. That's why they are same to each other. This one and this one. That's why you can write down this way. Okay. So now you prove that you can work with simple Boolean algebra. Now you are gonna do something more difficult one, complicated one. So now you have x and y. So you have x and y. So this becomes, so since it has two cases, that's why entirely they have 4 different cases, 0 and 0, 0 and 1, 1 and 0, 1 and 1. So now you want to calculate x plus y. So here this should be 0, this should be 1 and 1 and 1 because this is OR notation. Y plus 1, x, that is also same. That's why you can say that they are same to each other. So they are same to each other. Okay, so now you can go to the next one, 11. So now instead of doing the OR notation, now you are ready to go for the AND operation. So x and y becomes 0, 0, 0, 1. Y and x becomes 0, 0, 0, 1. That's why they are same to each other, like this one. So let's go to the number 12. So now you have 3 different variables. That's why you need 2 to the 3 different cases, x, y, z. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. So now you have x, y plus g. So this y plus g becomes 1, 1, 0, 1, 1, 1, 1. Now you are doing the OR notation with x. This becomes 0, the other becomes 1, 1, 1, 1, 1, 1, 1. Okay? Let's go to this one. This should be also same because over there x plus y becomes 0, 0, 1, 1, 1, 1, 1, 1. So now you have g lastly. G has 0, 1, 0, 0, 1, 1, 0, 1. That's why the first one should be 0. The other two should be 1. That's why you can see that this one is same with this one. That's why you can confirm that this is true. In the same way, you can prove the others as well. So those are all quite straightforward and easy to understand. So I hope you can do this one by yourself fully, and you have to understand this one entirely. So in the next slide, from the next slide, we are using these kinds of mathematical operation frequently. That's why hopefully for the next time you memorize these stuffs entirely. So let's go with one example. So this one, you can assume this is x, this is y, then this is same to each other. So this is another x, this is another z. So this can be denoted by x plus y, x plus z. So in this case, by the rule of this one, 15, rule of 15, this can be converted by x plus yg. So x plus yg by 15 rule. So x plus yg, x was a, y was b, g was cd. So a plus bcd. This is the final result, okay? So this is De Morgan's rule. So in this case, you only have two variables, x and y. That's why you have 4 different cases, okay? So in this case, this is all what we can have. So first of all, we have to calculate x plus y. So in this case, by the OR operation, we can get this result. Now you have complement, negation. Then we have conversion. So this is 1, the others are all 0, okay? And then this is x plus y bar, just like that. Now you have to look at this one. So now we have x and y. This is x prime, this is y prime. That's why you have this converged result. And then you are doing the AND operation. So AND operation, that's why you have this result. Finally, you can confirm that this and this are same to each other. That's why you can say that they are correct. And you can do this one by yourself, okay? That's quite straightforward, and same flow with this example result. So here we can also say that we can do the expansion of the De Morgan's rule. That's why you have more and more, you have more and more, okay? So you can look at this one. So next one, if you are very familiar with these kinds of Boolean algebra, then you can use this one in order to conduct simplification procedure of your logic gate. So let's look at these ones at first. So here they are same to each other, x prime y, and you have g and g prime. So g and g prime, okay? So before that, we have this one, okay? Number 7, this becomes 1. So number 7, this becomes 1, okay? So this one is this one, just like that. And then this one can be written by this one, by number 2, okay? That's why this is by number 7, this is by number 2, okay? So that's why you can get this final result, okay? Very simple. But when you look at this one, you have to understand that this one has same meaning with this one, because you are deriving based on the Boolean algebra. Then designing your circuit with this form is much more complicated than this one. That's why we need this kinds of simplification procedure when you are trying to design your logic circuit design. Now we're gonna see a much more complicated one, okay? Let's look at the first one. You have x and then negation. You have y here You have dot, it means that you can make the branch here. And you have G, so you have G and dot branch here and here. And then this result goes to here. So this AND gate got these three, okay? And then let's go to the second one. You have x prime, x prime, x prime. So this is prime, and then you have branch here and go to this way. Y is directly went to this gate, and in this case you have G prime. That's why you have G and prime, and then the result go to this AND gate. Finally, you have X and G. So X becomes here because of this branch, and then you have G. So G has this branch. That's why this can be here as well. Now, when you can compute all of them, and then you are doing the OR notation, OR operation. That's why you have OR eventually. Okay. Then you can say that the first equation is same with the this one. Okay. This is same to each other. Now you have to look at this one, okay? You have x prime at first, and then you have y. That's why you have AND gate. You have x and g AND gate. That's why you have x at first, you have branch, and this branch goes to this way, g goes to this way, and then you are doing the AND operation. Finally, you have OR operation. That's why this is OR, this is OR. That's why you have this result. Now this is same with this one. You can confirm. Then now you have to check that whether those are same to each other. If they are equivalent to each other, then you have to use this one, because this one uses less number of gate, which means that this is much more cost effective. Okay. So then, in order to check whether they are same to each other or not, you can easily write down the truth table. So when you calculate the truth table for the first one, then you will get this result. Please do it by yourself. And when you calculate the truth table for this one, then you can get this table eventually. Then you can confirm that they are same to each other. Okay? Then it means that suppose that you have options. Suppose that now you are logic designer, and then suppose that you can take this result, or you can take this circuit, or you can take this circuit. Okay. So if I'm the logic designer, I will go for this one, because this is much more simpler and easy to understand, and the number of gates are 4, and here the number of gates are 6, and this, if the number of this gate is $1 for each, then this is $4 circuit design, this is $6 circuit design, and even though their results are same to each other, this is much more expensive. That's why I will not use this one. I will gonna go for this one. Okay. So this is the thing. This is the thing why we have to understand Boolean algebra exactly. Once you understand Boolean algebra exactly, you can get some hint which can do the simplification of the given logic design. And then you can derive final logic design, which is much more simpler, which is much more cost effective. So today is the first week class. That's why this is a little bit simpler. And then you can see that we just went through these basic identification rules in Boolean algebra. So I hopefully you can prove all of them by yourself. You have to prove all of them by yourself, and then hopefully you memorize most of them. So for the next time, we'll go with more examples. With more examples, we can have a lot of flexibility. That's why once you are fully understanding these rules, then you can be ready for go for the next step. That's why in the first week class in logic design, this page 14 here is our final slide, and for the next week, week 2, we will go with more detailed examples. Before next Monday, hopefully I hope that you have to prove these rules at first, and then you have to calculate this one by yourself. And then you can confirm that both of them are same to each other. Then you are ready to go for the next slide. And thank you so much today for your attention. and we will meet all together in next week, Monday. Thank you.